Bismillahirrahmanirrahim. Welcome to the students to the second lecture of digital logic design. In the today's lecture, we will discuss the number system and the conversion among the number systems. In the previous lecture, we discussed a little bit about the codes. It was basically the introductory lecture about the codes. In the today's lecture, we will discuss the number system and the conversions from one number system to the another number system. This part belongs to the course learning outcome 1. In the last lecture, we discussed an example of a computer architecture or a basic computer system. Because the general purpose digital computer, you can say, is the best known example of any digital system, and our whole of the course is focused on the digital system. So the computer example is the most appropriate one to discuss different things. We discussed that there are 4 basic units in any computer system. First one is the input. The second one is the processing unit, which involves the control unit and the arithmetic logic unit. And then we have the output unit and the memory unit. These units always interface with each other to process any certain information or data. And depending upon what are the inputs, it also gives certain output values. We discussed each part in detail. We discussed that the input unit represents the input to the system or input to the general PC, like in a form of a keyboard or a mouse, while the output unit represents the output mode like monitor or the printer. And the memory, we discussed the memory hierarchy in detail. And then we have the control unit and the arithmetic logic unit. These are the part of the central processing unit. We will be discussing both of these units in detail in this course, and basically we will be studying the basic building blocks for the ALU and the control unit. First, we will discuss different number systems, that how a system and data is represented in a form of a different number system. Generally, there are many number systems. In the real world or in the common world, we are used to the decimal number system. We always use, say, in the addition, multiplication, division, or the arithmetic, we use the decimal number system because it is, you can say, a real world number system. Our common conception or the manipulations are basically based in the decimal representation. So first thing what we will do is in this course, whatever the number we are representing, we will always represent it in this kind of a form. We will represent that number in the form of a binary, in the form of certain brackets, and this number will represent is radix, you can say, or the base. So for the decimal number system, we have a base 10 or radix 10. R is equal to 10 here. Similarly, there is also another number system which is known as the binary number system. In the binary number system, we represent the system in radix 2 or the base 2. Similarly, in the octal number system, we represent the system in base 8 or R. Similarly, we can represent many other systems. The one common one is the hexadecimal system, in which the base is 16. So these are the common number system which are used by different system, or you can say the different architectures on the digital design. Because we are more familiar with the decimal one, we will always try to relate all these number to the decimal domain. One thing is sure that if you see these number like this, the decimal, these 4 and these 8, they represent a digit. Say this is the number system digit. The 8 represents a separate digit, while the 4 represents a separate digit, and the 48 combinedly represents the number. Similarly, for the binary number, this 0 represents a separate digit, the 1 represents the separate digit. And for the octal 2, this 4 represents a separate digit, while 5 represents also a separate digit, while the 45 combinedly represents this octal number, and this 10 combinedly represents the binary number. For any number system, the number of values any digit can obtain is always from 0 to r minus 1. In the decimal number system, any digit, the maximum value of any digit is a 9. So we can represent any number between 0 to 9 here. Similarly, in this place, we can also represent any number between 0 to 9, and number cannot exceed them. So for the binary number system, we have a maximum value of 2. So for in this case, our system will have only two number. Each digit can be represented in either 1 or 0. So it can be value for any binary number. The value could be either 1 or 0. Similarly, for the second digit too, it could have a value of 1 or 0. And now for the octal number system represents that this base is equal to 8. So in this case, any separate digit of the octal number system is represented between 0 to 7. So it cannot exceed the value of 7. So these are just the basic understanding or information about how we represent a given number system. Say if we have represented an octal number system and we write here as 49, it would be incorrect because the octal number system has a maximum value of 7. Now we will see that how generally we represent any given number in a say decimal representation. First, what we do is we find the decimal point. In this case, the decimal point is represented as here. And now we will be representing the coefficients. If we go towards this side before the decimal point, we will increase the coefficient as A0, A1, A2, A3, A4, A5. While if we go beyond the decimal point, then it will be have A minus 1, A minus 2, and A minus 3. All these numbers are basically multiplied by the power of 10 if we are dealing with the decimal number system. For example, let's say we have a number, we will represent in a generic form like this one. So the upper line here is representing the points which are before the decimal points like this, and the second row is representing all the numbers which are after the dotted line. You can see by the coefficients here. So this is how we represent any given decimal number in terms of 10, 100, thousands. We know that the base here is 10. That's why this power is 10. If you see that from as we move away from the decimal point here, we will be increasing in the power of 10. We have a 10 power 0 here. Then we have 10 power 1 here. Then we have 10 power 2, 10 power 3, 10 power 4, and similarly 10 power 5. And then we have the decimal point, and after the decimal point we will be having a power decreasing in the form of tens. So we will be having 10 to the power minus 1, then 10 to the power minus 2, then 10 to the power minus 3. And similarly we will be multiplying them with all the coefficients to get the number. For example, we have a number like this. This number is represented in a decimal form. It has 4 digits, 2, 9, 3, 7. We will be representing this number in a form of separate powers of tens. So this is a common representation. You have studied a lot of time it before. This term is that first because the decimal point here is after 2. So we generally have a decimal point like here too. So as we have discussed up here, that as we move away from the decimal point, the power of the 10 will increase. So we have 10 power 0 here, 10 power 1 here, 10 power 2 here, and 10 power 3 here. So what is this actually? This is 10, 100, 1000, 10,000. So this is how we generally increase that. 10 power 0 means 1 unit, 10, 100, 1000. So this we will get. So we will just calculate the values of this 10 power here. This is unit, 10, 100, and 1000. And what we will do is we will simply multiply with them the coefficient values, because the maximum value here is 7 into this will represent the 7000 term. 3 into 100 will represent the 100 term, which is 300. So this is 7000 and this is 300. This 9 into 10 will represent 90, which is represented here. And then last 2 into 1 will represent the 2. So by adding them, it will give us this result. So any decimal number system is generally represented in this manner, which you should be very familiar with. We represent the number in the form of unit, 10, 100, and 1000. We simply increase the power as we move away from the decimal point, and we keep on multiplying all the coefficients. So this term will give us 7000, this will give us 300, this will give us 90, and this will give us 2. Now we will be discussing a little bit about the conversion system, that if we are say in a base 8 and we want to move to base 5, or we are in a decimal number system base 10 and we want to move to a binary number system, then how we can proceed this, because all the digital systems are mostly based on the binary logic, or means you can say the binary number system. So for any binary number system, any binary digit can have two values. It could have a value of either 0 or 1. So we should know what is the base value here, which is represented by R. As we have seen that for the decimal number system, what we do is we multiply the coefficient with the base to the power n. Say this is our decimal point here, so we will keep on increasing the value because we haven't written R0 here, because R0 value is always equal to 1. So whatever the decimal, whatever the base here will be written instead of the R, and then we will keep on increasing this power till the value of n, or the maximum value, or the coefficient value we have. So this is the same equation we discussed in the last slide, but the only thing that is changed here is that instead of the 10 written here, we have written R. So this is a generic equation for any base number conversion. And we know that for any base value or for any number system, the maximum or the minimum value is 0 and the maximum value is R minus 1. Say we have a number which is represented in base 5. In base 5, it is represented in this form, 4021.2, but we have written here it is represented in base 5. So we now want to represent this number into a decimal form, because commonly we are used to dealing with the decimal number space. So that's why we are converting this into the decimal part. So what we will do is, just in this equation, we will simply put the values of R and the coefficients. So we will start with the decimal point, which is here. And then first we will keep on increasing the value of the base 5 here. It's 50, 51, 5 square, 5 cube, and we will simply just multiply with them. The first coefficient will be multiplied with the 50 term, 5 power 0. The second coefficient 2, which is 2 here, will be multiplied by the 5 power 1. The third coefficient, which is 0, will be multiplied with the 5 power 2, and the last coefficient, which is 4, will be multiplied by the 4 into 5 power cube. And similarly, after the decimal point, we can see that we have only one number 2, so it will be multiplied by 2 into 5 power minus 1. So if we just calculate all these values, this will result in this term 511.4. So this is how we can represent any given number system to a different number system. Say in this case, what we are doing is we are representing a number system which is given in the radix 5 into a number system which is given in a decimal form or base 10. So if we are moving from base 5 to base 10. So in this way, this is both of these numbers are equivalent. This 511.4 is equal to this 4021.2. We will simply just add these numbers and this will result in. So basically both of the numbers are same, but they are represented in different number system. This is represented in a decimal number system, while this is represented in a base 5 number system. Similarly, any other number system can be converted into the decimal in the same form. Say we have a number which is in octal 8 form, or a binary number system. What we will do, say if we have a number in octal form, say 8 here, we would have only changed the value of R here. Instead of the 5, we will write 8. Similarly here Similarly, we will write 8 here, and similarly 8 here. So this is a general representation. It could be used to convert any given number system to a decimal number system. And now we just for another example, we will convert a number which is represented in a binary number system into a decimal number system. We can see that in this binary number system, we have 1, 2, 3, 4, 5, 6 binary digits. Each binary digit we now can have a value of either 1 or it could have a value of 0. So if we want to convert it into the decimal form, we will use the general equation which we represented in the last slide. What we will do is we will have 1 into 2 power 0, which will give us 1. Then the next term is 0 into 2 power 1, which will give us 0. So it will have no effect here. Then what we will have is 1 into 2 power 2, which will give us 4, which is represented here. Then we don't have the next term, and then we will be calculating the last two terms. This will represent 2 and 1 into 2 power 4, which will give us 16, and 1 into 2 power 5, which will give us 32. So in this way, if we add the result of each component separately, it will give us a decimal number like this. So actually this number and this number both are same. They are just represented in a different number system. This is the decimal number system and this is the binary number system. Because we are dealing with the binary number system, and the whole of the digital computer system or the digital domain concept is built on the binary number system. So we have to very deeply study what's the importance of this number system. Say if we have a single digit, if the n represents the digit. Say if we have a single digit binary number, what we will get in the result or equivalent, say it have a maximum value of, or you can say in the power of the 2 if we will discuss here. So what we will have a value here for the 1, what we will have the maximum value for the 2, 3. Just say it's like 2 power 0. The 2 power 0 will give us 1, 2 power 1 will give us 2, 2 power 2 will give us 4. Similarly 2 power 3 will give us 8, 2 to the power 4 will give 16, then 32, 64. Similarly, if we keep on increasing them, we will see that for every power of 2, we increase in this way. It's like now, it's not like just doubling, but it's actually the power of 2 increasing. Say this 1, then 2 here, 4, 8, 16, 32. So if we increase a single bit in our system, we are increasing the number of decimal number or the equivalent number that we can represent in our system. Because if we extend say more number here, then it means we can represent a much bigger number than this here. You can see that in this case, when we increase the number, we don't have a usual structure like once we follow in the decimal, like 10,000, 20,000, 1 million, 1 billion. We don't have these kind of values here. You can see that this structure is a little bit different. Why it's different? Because it's not to the 10 to the power, it's power of 2. So by increasing in the power of 2, we will get these values. So as you know that if you use any memory or access any location in a memory in computer system, we have different terms. Like we represent the 1K term as 1024 MB or KBs in this form, because it's not 1000, because it's to the because power of the 2. That's why we represent it in this kind of way. So like if you're representing say a 32 MB, it would actually be formed this kind of a value. So it depends on what value of the two is that you can represent the maximum value. This table is very important in understanding the whole concept of this binary number system. Say for a single binary number system, you have just a one digit binary number system. For one digit binary number system, you have maximum value of the coefficient that you can have there is 1. So the maximum value you get there is 1 into 2 power 0. So what will be representing that value? It will be representing 1, a maximum value of 1. Now say if we have a 2 binary digit number, just assume that we have the first two value here and both of the coefficients value are 1. In that case we will have 1 into 2 power 0 here and 1 into 2 power 1 here. So in that case what we will be representing here, that in that case we will be having a maximum value of 3 in that term, because for 2 power 1 we will get a maximum value of 2 and for 2 power 0 we can get a maximum value of 1. So by combining 2 plus 1 it will give us a maximum value of 3. So for any two digit binary number we can have a values in the range of 0 to r minus 1, or you can say 0 to 3 2 power r minus 1. We will get these values. Say now if we have a three digit binary number, a three digit binary number with all ones is equal to 7, because if we calculate the values in a similar way that we calculated in the last slide, or we can use this type of terminology here, we have a three digit number, and in that case we will have a maximum number that is represented here is 7. So we can represent number from 0 to 7. The total number of number represented in this will be equal to 8, because if we count the 0 the total number will be 8. And if we see that the 2 power 3 or 2 power cube is equal to 8. So in this way we represent any given binary number system. We will be discussing these examples in more detail in the next few slides. But kindly do stop for a few minutes and just try to understand this table, that how by increasing the value of 2 we get this result. Now, in the second example or second type of examples, what we will be discussing is that we will be now converting from a decimal number system to an other base system. What we have done till now is we have converted a number which is given at any base, say base 2, base 8 or base 5, into decimal number system. And now we will be doing the reverse part. We will be converting any number system which is given in the binary in the decimal form to any number in the binary form. Say in this example we are converting into the binary form. Say we have a decimal number system which will represent a 41. So 41 is represented here. This is a decimal number, and now we like to convert it into the binary number system. So in this case how we proceed is we divide that decimal number system by the base of the number system that we want to convert, because in this example we want to convert it into binary, so that's why we have used 2 here. So in the first part what will we do here is we will divide this 41 which is in decimal number form into by 2. So when we divided it by 2 we had a remainder of 1 here. Now we will divide it by 2, and now we have a remainder which is equal to 0. Then we again divide it by 2. This will again represent a remainder 0. Then we again divide it by 2. We will get a remainder of 1. And finally we will divide it by 2. We will get 1 0. So in this way we will divide any given decimal number system to the base of the number system in which we want to convert. In this case it was binary, so we are representing here it as 2 here. So now the answer here will be by following this arrow. We will move from here 1 0 1 0 0 1. So this will give us the binary number system. So this is actually our equivalent of the decimal 41 in the binary number space. This number in the binary number system and this in the decimal number system both are now the same. We have just converted from this space 41 to this in the binary. What we do is we will just divide that number by the base, which is a 2 in this case. We will keep on dividing it till we get the least number here, and we will follow this direction. We will first count this one here, then all the remainders in this way. So this is the answer to our system. And similarly, you can apply this example to any other systems too. Say if you want to convert 41 into a say octal number space, and for that case then we will be dividing this 41 by 8 here, and we will follow the same procedure. We will first write the remainder and then the last one here, and then all the remainders in this sequence, which will give us the result. Now in this example we have a system which is representing only in the floating point. We have represented a system represented at 0.6875, which is represented in a decimal number space, and now we would like to convert it into the binary form. It is slightly different from the process is slightly different from the one which we discussed in the last slide. The one in the last slide was before the decimal point, and now this method is for the after the decimal point. In this case, what we'll do is we will first multiply this number in the decimal system to the base of the number system in which we are going to go. Say because we are going to represent it in a binary form, so that's why we will multiply this by 2. So what we do is we represent multiply it by 2. We will get an integer result of 1, and this part is the fraction part which will come. So in this case, what we will do is we will write the value of the coefficient, which is a minus 1, you can say here, which is equal to this integer part here. Now we will keep on moving the same process, and now this time we will multiply this term with the 2. Now multiplying this fraction here with 2 will give us the value of 0.750. In this case, we don't have any integer component in here, so that's why the second coefficient value becomes 0 here. And for the third one, we will multiplying by this one. We multiply this one, we will get 1.5. So we have one integer value here and 0.5 here. So this will give us the coefficient value of 1. And for the next, if we move on, we will just be multiplying this term with the 2. If we multiply 2, we will get 1 here, and now we have a 0 value in the fraction. In this case, the A4 or the last coefficient will equal to 1. So now if we want to write this value, now we will follow this sequence from top to bottom, because in the last one we follow from bottom to top. Now for the after the decimal point, we will follow top to bottom approach. So we will first write 1 here, after decimal we write 1 here, then 0 here, then this one will become here, and this one will become here. So what's the stopping criteria for this one? Generally, because it's not possible that always we will get a 0 here. It's just for this example, it's not possible maybe for all the examples, because we could get a number which may not have a 0 fraction even if we multiplied 100 times by 2. So in that case, there must be some accuracy level given to you, say that you have to calculate the number up to 4 decimal point accuracy. So in that case, you will be only calculating these 4 values. So generally, if you have a fraction in say 3 or 4, if the fourth term you say stop here, it's fine. But if it's not given, then I think so third or fourth terms are enough. Up to 3 points or 4 point decimal accuracy is enough. Now what we will do is we have in the last two slides, in the current slide and the last one, what we did was we converted a decimal number system into a binary number system. In this case, we had a number system which was represented only in the floating points or after the decimal points. While in the last example, we had a number in which there was no floating point. So now what we will do is we try to combine the both of these results, because both of them have a different procedure. In the last one, we divided it by the 2, and in this one we multiplied it by the 2, and the last one we use the value of the remainders, and in this one we use the value of the integers. Say if we combine the result of both, say if we have in the last slide we have number 41, and in this this slide we have number 0.6875. If we combine both of them, this number is combinedly represented here as base to 10. And now if we if we want to convert this number into the binary number form, what we do is we have already calculated this term. We have calculated this term from the last slide, and we have calculated this term in this slide. So we will just put the decimal point. We will first put all the values that we calculated before that, and we will then put the values of the values that calculated after that, means after all the floating point values. So we will representing this number which was in decimal form into the binary form in this manner. So if we have a system, say we want to convert this number into any other base, we will simply multiply it by the base of that number. Say we want to represent it in base 5, then we will be multiplying it by the 5. So in this way we can represent any given number which is in a decimal system to any representation. We have done the example of a binary system here, but it is easily applicable to all the other number systems. The process remains the same. Just in the last slide we will divide it by 2, and in this slide we multiply it by 2. So if we want to represent it as an octal, then we will be dividing it by the 8 and then multiplying it by 8 here. So this will give us the result. This table gives us very good result or good view of how a decimal number system is represented in a different base form. Say this is a decimal number system which is represented here as this. The first number is 0. Its equivalent to the binary number system has been equal again is 0, because all the coefficient value is equal to 0. If we apply all the equations from the last slide, it will give us the result of 0. Similarly, its equivalent in octal base is 0, and in hexadecimal again it's equal to 0. If we are representing a 1 in a decimal number system, then in binary we can represent it as this way, octal this, and hexadecimal as this. So you can see that for 0 and 1 case, all the representation are the same. There's no difference among them. It is 0 here for all these terms, for 1 here, all the terms. Now the difference will be shown. For the second term, say 2. If we convert the 2 into binary form, we can represent it as 0, 1, because it is here 2 power 0 and this will be 2 power 1. So multiply by 1 into 2 power 1 will give us 2. So 1 0 is basically equivalent to 2 in the decimal number space. In the octal number space, 2 is equal to 2, because till the value of 7 both have the same value. Similarly for the hexadecimal. For the 3, if we want to represent the 3, both values of the first 2 digits are equal to 1. So this will represent, if we convert it using the formulas which we have discussed in this lecture, this will be equal to 1 into 2 power 0 plus 1 into 2 power 1, which will result in 1 plus 2 will give us 3, or equivalent decimal. Here. For the next one, for the 4, because if we are using the 2-digit binary number, and the 2-digit binary number, we can express a maximum number of 3. We cannot express any maximum number than 4, because for the 2-digit number, the maximum value of any binary number could have is 1 1 when the both of the digits are 1, and when both of the digits are 1 we have a result of 3. So the maximum value that is represented in a 2-digit binary number is 3. For a 1-digit binary number we have discussed it's 1, but for the 2-digit binary number it's 3. So if we want to represent any number greater than 3, we have to include another binary digit. In this case we have included another binary digit. So if we convert this number 100 into decimal equivalent, which we will have 0 into 2 power 0, 0 into 2 power 1, 1 into 2 power 2. So 1 into 2 power 2 will give us 4. Similarly for the 5, and again in the case of 5, if we represent it as 1 2 power 0, 1 into 0 into 2 power 1, 1 into 2 power 2. So this is basically 4 plus 1, 5. So this will give us an equivalent of 5. Again similarly for 6 and the 7th term. And now for the 7th term you can see that if all the 3 digits are utilized. So if we have a 3-digit binary number, or we can say a 3-bit number too, we will also be using another term for the binary digit, which is also known as the 1-bit. We will be discussing it later. So for each bit or each binary digit, we are representing all ones here. So for a 3-digit or 3-bit binary number, the maximum value that system can achieve is 7. The minimum value is 0 and the maximum value that it can achieve is that 7. For representing any number greater than this, say we have to represent 8. In this case, for representing 8, what we will do is we will add another binary digit or a binary bit here. So we will add an additional bit here, and then we will. Now if we convert this into the decimal number space, what we will get 2 power 0, 2 power 1, 2 power 2, all these terms will be 0. And what we will be having here is 2 power 3, which is equal to 8. So now we will get. And now if you look at this term here, in the octal number system, for the 8th term, it is again a bit different from this one. Why? Because the maximum number that is represented in a base 8 or the octal number system is 7. It cannot have a value of digit more than the 7. So in this case, what we will be requiring another octal digit. So in this octal digit, we will have we will be now utilizing the second octal digit here. So the 8 is represented in octal base as 1 0. Same process by which we have calculated the binary. We multiplied it by in 2 power here. We have to multiply it by the 8 power here. And then we will calculate the 9, 10, 11s here all the time. And then we have another number system which we call the hexadecimal number system. And for the hexadecimal number system, we can see that after the 9th term, the 10th equivalent of decimal is represented as A. The 11th equivalent is represented as B. The 12th equivalent is represented as C. 13 as D, then 14 as E, and 15 as F. So in the hexadecimal system, we represent a number from 0 to 15, and if we include this 0, then we can represent 16 numbers in it. So this base represents that it can represent total 16 number. Similarly, this base represents number from 0 to 7, so total number represented here is 8. Similarly, for any binary digit or a binary bit, we can represent 2 number here, 0 or 1, so total number here are 2. So in this way we relate the different number system to the decimal number system. So you can apply all the formulas on which we have discussed in the last slide on any of these bases, and you will get this result. You can easily get from this result, and you can also apply the reverse part here and get this result again back. Now we will be discussing a few examples for the octal and the hexadecimal number system. We have seen that if we are representing any numbers system, we have to represent it in a different kind of form or base same. This is represented here in base 2 and this is represented here in base 8. If we now see that the ways that first locate the decimal point. So this is the decimal point here. First we will have this. This 3-digit or 3-bit binary number represents the equivalent in the octal domain. So if we just convert it here, we will get that this 011 in the this value here is basically representing the 3 here. Similarly, if we use the term 101 in the binary and convert it, it will give us the maximum value of, it will give us the value of 5 here, because 2 power 0 here, 2 power 1 here and 2 power 2 here. So it will be 4 plus 1, it will give us 5. So we will have 5 here. This will have 1 here. This will have 6, and this 10 represents the 2. So, and in the similar way, we can represent this number in form of after the floating points, because this now 3 digits combinedly represent a single octal number. And we know that if we have 3 digits and we represent them in the binary, then the equivalent decimal or the equivalent octal number will be equal to 2 power 0, 2 power 1 plus 2 power 2, which we will combinedly give us 7. So this will be represented as 7. This is given as 0, 0, 1. So 2 power 0, 2 power 1 and 2 power 2, which will give us 4 here. So we will have 4 here. This is all 0, so it will always again be it will represent the 0 here. And then we have the 6. Sorry, there is just certain miscalculation. Actually, this number is here, its location is here because this is 6. So actually this number, kindly just interchange these two numbers. So this is the 6 here, 110 will represent the 6 here, and the last one will be the 0. Similarly, we can represent any number system into, or say a binary number. We can go from binary number system to a decimal or hexadecimal number system. In this example, we will be dealing with the hexadecimal number system. For the first, we will locate the decimal point. It's here. Now the value here is 1011. If you refer to the table, if you refer this value to the table which we discussed in the last slide, the 1011 represents the value of decimal value of equivalent to 11. So we said that in the hexadecimal we will be representing the 11 value as B. So we will be writing here as B. This number corresponds to the 6 and we will get 6 here. So basically in this case, in this conversion, this set of 4 digits are representing a single digit for a hexadecimal, because a hexadecimal number requires 4 digits in binary to be represented. Just like in the octal number system, it required a single digit to be represented in 3 binary digits or binary bits. In a hexadecimal number system, it is required that the equivalent binary number system is represented in 4. Because otherwise, if it is represented as 3, then it cannot represent the other values greater than 7, like 8, 9, 10 or 11. So that's why we are representing this in 4 bits. So if we use, say, this is equal to 2, and if you see this 1100, this will give us the value of 12. The 12 is represented in the hexadecimal as C, so we will write here as C. Similarly, if we go the other way around, if we want to convert this octal number system to a binary number system, for each digit, because this is an octal and each octal requires at least 3 bits, so we will be representing it in 3-3 set form. So this 6 is represented here as 110. This 7 is represented here as 111. This 3 is represented here as 011. Then after decimal point, will be again we will be representing them in the set of 3 bits, because the maximum number represented in 3 bits is 7, which is also the maximum of the octal number. So that's why we have here, this will be representing 2 and this will be representing the 4. Similarly, if we have any given number in the form of say hexadecimal, and in this case we want to convert that hexadecimal into the binary number system, what we will do is we will just first assign the number of bits, because each hexadecimal bit requires at least 4 binary digits or binary numbers. So we will be representing each number in the form of 4 bits. So for 3 we will be representing it as 0011. 0 is represented as 0. Then we will represent it as 6 as 0110, and after that we have a value of d, so which is equivalent to 14, so which is represented in the binary as 1101. So in this way we represent any number system to a given number system. In the case of hexadecimal number system conversion, we would require the number of bits for the binary representation to be equal to 4. Otherwise we will not be able to represent. And similarly for the 8 or the octal number system, we will be requiring at least 3 binary digits to represent any equivalent octal number system. Kindly do read these pages from the book and try to solve all the examples given in the books in these pages. It will give you a better understanding of the topic. Thank you.